groups are related to permutations of objects, right? You can think
Correct.
of them equivalently as that. Does that mean that the Fourier transform is somehow connected to permutations of objects? Like somehow the Fourier transform is a combinatorial operation?
No, but what I will teach you now is answer to your question. So right now we'll be looking at a triangle in a plane, but its actual symmetry is the largest possible symmetry of three objects, which is 3 factorial, which is so-called symmetric group or group of permutations. When we look at cyclic rotations, they're all permutations because, we permute elements. We move by one step and every element gets permuted is the next one in the sequence. So that's a special permutation, but it's very restricted. We only allow neighboring elements to, replace each other in a cyclic order. So it's a very small subgroup of the symmetric group of all permutations. Now, representation theory of symmetric group of all permutations is harder, but it suffices to understand the first non-abelian example, first example where the two operators don't commute, rotations and flips, reflections don't commute. And, from then on, one can build all of them. Now, what's amazing about this video that you watch is that, so we know that if I have 3 objects, I have, 3 factorial, 6 permutations. If I have 4 objects, I have 24 permutations. So I know all these huge numbers because factorials grow very fast. So I know, like the maximal number of things that could happen under operation on a finite set of n things, objects, whatever. And that's this kind of permutations. Now, one thing that one learns very quickly, and that video says it very quickly, is the important ones are so-called simple groups or groups which don't have subgroups. So it turns out that when you look at a cyclic group of 4 objects, then it turns out that if you step every second time, then you have a cyclic group acting on 2 things, which is a subgroup of the 4, because it satisfies all the axioms of the group. If you only take the even parts, you will stay even anytime you multiply the 2, etc. So you get very quickly this notion that, whenever I have a group, I should look at its subgroups. And that thing explains it well. And, what's amazing about that video, it tells you that, what's amazing is all this stuff comes from Renaissance and French Revolution. So in Renaissance, there were mercenary professors, what's called tenured professor now, but there were mercenary mathematicians who were taking roots, cubic and quartic roots, but they couldn't do quintic. Then in French Revolution, the young Frenchman invented group theory, subject I'm teaching you now, to show that if you try to do quintic, now the reason why they could do quartic is because quartic has a subgroup of 2. We know that now, they didn't know that then, right? But they invented complex numbers. They didn't want them, but that's, amazing invention. It turns out their failure to do solve analytically, in terms of nth root and multiplication and divisions, write the formula for 5th root, is what gave birth to all the group theory I'm teaching you now by a young French revolutionary called Galois. He was just like a student in, Black Lives Matter movement, and he met a nasty person who killed him in a duel for no reason whatsoever. So we lost this amazing mind. But he invented he showed that when he tried to do the 5th root, and that video is nice and explained it has a prime group 5, and for that you can prove that you cannot write roots in the way they used to do that in Renaissance. So everything comes from there. But for our purposes, we don't have to worry about, that's another level. I just want to teach you some beautiful stuff at the grade school level and not at the graduate school level.